everyone can see you. And you can go.
Oh. Yeah, you can see the presentation, I hope.
Yes.
So I will start the presentation mode.
That would be great. Thank you.
You have the presentation mode in view of you, in front of you?
I just see a normal presentation,
yeah, now
including
it's
the.
started.
Okay.
Yeah.
That's fine.
Okay. At least it's working on my side, so I hope it's working on your side.
Okay.
Well, welcome. Good to be here again with Aqua Control. A little bit digital, but I think it has the same intent and it's still enjoyable. I would like to use the allowed 15 minutes to zoom into a little bit detail about zero energy soil remediation. We have applied this technology for some recovery of free products. And what we've done is instead of using the normal energy consumption by mains, we used solar and wind energy produced on the site itself. So happy to share some experiences. About myself, I'm both been working as a consultant and contractor for quite a while. Field of contaminated land, still very enjoyable field, I think. And projects done in multiple countries, which more or less enhance the experiences. And now at the moment I'm working with HMVT, a company who's already 30 years involved in this process, and their main activities are still institutional remediations, but also water treatment. And projects are basically in a lot of places. What I want to tell you about is I would like to start with something out of the ordinary, just to say where are we now with energy and looking into sustainable manners of remediation. After that, I would like to tell you a little bit about the project details and then move on to the process, the design process on this particular site. Why would we on this site use zero energy? A little bit about project operations and design evaluation to conclude with some conclusions. I think that if you look into environmental technologies, we are now really in a transformation phase. We have, when I started in the business almost 30 years ago, we did the first very detailed assessments about biology. What does biology do with contamination in soil, in water? And then we slowly moved on to use those biological aspects when we designed remediation, and we use it as a remediation tool. And you can see that in the last decade, the know-how about solar and wind for energy production has also, has been evolving quite rapidly. And together these two, more or less make us, they provide the tools to redesign conventional remediation methods away from high energy, basically endless energy about it. It's the main, you just attach your system to the main system and then it can run. And we are slowly moving not to use the energy from the energy providers, but to use the energy we can use on site. It's particularly interesting if you look into in situ remediations, what this means for in situ remediation. They are, I think, quite particularly suitable for this transformation because the processes which they aim for are not as much dictated by energy input, but much more by soil properties. As you all might know, is that water flows and there is a kind of resistance. And you can pump harder, but at a certain moment you will see that there is no effect about pumping harder. You're dictated by the flushing rate of the soil, of the water. So there's a limit to what energy can do. And you can also see that a lot of in situ remediation processes, they are not basically performing better when you have continuous action. It's often better to have a discontinuous process, 3 hours working, 10 hours doing nothing, etc. And what you also have learned is that time planning considerations, they are less severe with in situ remediation. You can say, well, it's accepted that remediation using in situ technologies will require time. Nobody expects you to finish the project within 2 or 3 weeks. Of course, there is a planning, but the planning for a project is more dictated by the design phase and the approval phase than the actual in situ time requirements. Which is also important is energy consumption. If you look into an average in situ remediation, and as a company we perform multiple at the same time, we know that they consume a lot of energy. Of course, a lot of contracts, they say, well, the client provides the energy, but basically there's an energy consumption. And that is quite a high amount if you consider it on a year, especially if you compare it by an average household. So there is things to say about why not looking if in situ remediation can be addressed in a different manner from an energy perspective. Again, if you look into the most applied in situ remediation technologies, you see that a lot of them, they operate better if not operated continuously. Soil vapor, you can have a discussion about it, but air sparging, there will be no discussion about it. It's quite sure that this continuous process is better. Same applies for free product recovery of multi-phase extraction. And 10 years ago, we all learned about clever or smart pump and treat. It's often better to have not a continuous process. But that's... I want to move on to the project details, and later on I come back to how we apply energy in the most efficient manner to achieve the highest project or recovery result. If you look into the project details, it's basically there are two sites quite near to each other. We address them in the same manner. They are all the purpose of the project is to test an approach, and basically the main issue here is to recover free product. The free product is at a relatively low level, so it's about 30-40 meters below grade, which is quite unusual, but is due to the particular soil buildup on this site. And what you see also here is that when we start thinking about it, basically the technologies we use here, they will be in situ. As you can see from the depth, nobody is considering excavation, so that's easy. If you also here look a little bit about the remediation systems we installed, you see a lot of wells aimed to the purpose of the well is to recover free product. And you see sparging wells, which is basically meant to mobilize, create pressure differences, which would enhance the flow of the product to the wells. That's the design, the remediation design. If you now look into the energy details of the project, we had not even extensive discussion, but what you notice is that if you look into the energy consumption, we need powers for the logics to control basically the alarms, etc. Basically, fairly simple wind power can provide it. You have about 500 watt consumption, and you have this solar, and you can see here the amount of solar panels installed is relatively. It's not that great yet. It's more than an average household, but it's not excessive. We calculated that with this amount of solar panels, you could create 2 kilowatt hours. A little bit back to the design process. If I refer to zero energy, I mean I don't want to use the mains. So the power supply of the main company or the electrical company is not in order. It has to do with the remoteness of the project. It's basically off-grid. And it's in the area of natural beauty. So there are already two things that makes you redesign a conventional approach. A temporary power supply, mostly provided by an aggregator, or it's not an option because it creates just too much noise in a natural beauty area. Apart from the CO2 production. And the construction of a new power supply is not, as you all might know, it's very costly and it's also very intrusive. So combine that with the discontinuous operation of in situ technologies, there's basically no objection to look for a zero energy approach. And what we do with in situ remediation technologies on this side is we use them for free product recovery and for the mobilization of product toward the wells. The energy conversion, that's what we are learning at the moment, and for the last 5 years is how to apply energy, which you have generated locally. Is the best method electric, or is the best method other? You know, we are all used to solar panels creating electrical energy for your house, for your car. But is that the best option? That's part of the design process. If you can see if there's a type of energy conversion which is the best for a particular remediation approach. For in situ systems, basically we cannot. We need electric just for the controls. We cannot lose that. But in situ system itself, electric is not the best method. Batteries itself, they are fairly costly. Loading time is extensive. And I don't even talk about the weight. A better option here is just to use pressurized air. I will zoom in now, explain a little bit how that works. We have the solar panels. We apply a conversion technology, and that generates an air compressor, and that generates compressed air, basically. And the compressed air is stored at a certain level of pressure. We use 4 to 5 bars. And itself, the pressurized air is used to run the sparging system and to use the product recovery systems. So basically, this is the design using energy converted into a useful manner so that you can operate the in situ remediation. We started the project in November 2020. I want to share this learning experience with you. That's not the best time for solar. So it took a lot of adjustments on the side, but at the end, we got the project and the systems running. We learned a lot also about exposure. What you see is that exposure and solar panels are very critical. It means basically that you can have an operation on a day, not for 5 hours, but for 8 hours, just by looking which is the best exposure. And that's very site specific. You cannot have a generic approach for that. Since January 2021, we have been operating. We only operate during daylight hours. Also has to do with the area and the natural beauty spot it is. And what you also see is that since January, we have been able to increase the operating time from 4 to 5 hours to more than 10 hours, even now almost 12 hours a day. So that tells you a lot about what is possible. If you look into what we have achieved on the site itself, we have tested various parting scenarios and extraction scenarios to see what result in the best recovery of free product. That went well. It's a very problematic site due to the very compact clay that is present in very deep levels. But until now, we have been able to recover 100 liters of product, and we get better all the time. That's the main purpose of this project, is to test which is the best ways of applying technology in this specific field. Basically, that's hardcore in situ remediation technology. We have combined here with using solar and wind energy. What we have learned is, and that's getting back to the start of my presentations, is that for this site, energy is in which way is not a limiting factor. The energy doesn't define your success. Always the soil properties define your success, and that's quite recognizable because that's always the case with in situ remediation. Looking a little bit further, if you see that this works, basically it's easy. I think I'm quite convinced that zero energy, so using solar and wind to create energy on site, is effective on this site, but it can be more effective on a lot of sites. At the moment, we are thinking about optimizations, but that's basically what you always do in situ remediation. And also for the energy production on this site, we look into the the solar panel. Polar panel is not the right word, but solar panel exposure. As I mentioned, it's always site specific, and with a quite easy adjustments, we still are able to increase the solar panel rate for another 25%. This basically will help us to have a faster loading time. So basically you are able to run more cycles a day. If you look at future optimizations, we have specifically not used batteries on this site. We don't believe in batteries for this particular operation, in situ operation. We think that pressurized air is much better, much safer, much easier. And also for this site, you can easily expand the capacity by installing more pressurized, more vessels. We have some conclusions. I think that at the moment, that all the technologies are available for transformation, meaning that apart from understanding biology, we now have learned to understand what energy, local energy production can do for in-situ remediation. Combining those two, I think there are more and more sustainable soil remediations possible. The intelligent design, it sounds very fancy, but indeed we are still need intelligent design. They are available, a lot of software is available, and of course we have still see new energy technologies. So if you summarize it, not only biological processes are now qualified as sustainable, but I think also zero energy can now be qualified as sustainable. We don't use energy. We create energy and we use it to remediate the soil. So zero energy is in most cases quite a viable approach. And what is for me important to share with you is that if you look into the technology, it works. But it now also means that if as a consultant or as a remediation option, if you define remediation options, you should also look into energy and how you can create local energy by wind, by solar, and use it to perform the in-situ remediation process. Overall, I don't think the total remediation time will change that much. And at the end, you can, if you apply this more and more, you will see that that also governments or environmental authority will start to accept the technology more and more. And I think it completely is in line with a lot of companies or governments who want to reduce their energy and their carbon footprint. I want to thank you. I think this is all I have. So if you have any questions, please let me know.
Thank you, Paul. I don't see any questions coming in yet, but maybe we should give it a minute. I mean, we're good on time. What I was wondering is if you, in the remediation process, regard that sometimes you get a waste stream, and that waste stream also needs to be treated, and obviously that can require some energy. Is that part of your sort of zero energy consumption goal, or?
Yeah, well, here we did a recovery of free product, and that's in this case the waste stream, and that's due to the already concentrated manner of product. That's very easy to tackle. It can even be used for energy production itself because it has a high purity. So that basically there wouldn't be any residual product. But I can imagine that in the future, if you look into these systems, which may apply, for example, activated carbon as a purification method, indeed, you still have there an energy optimization process.
Yeah, I mean, the same holds probably for the formation of the granular activated carbon itself.
Exactly. So there are a lot of angles to look into remediation and what it consumes. But we can see that energy for in-situ remediation, just to keep the systems running, is quite significant.
Yeah.
It's quite impressive how much energy you need just to run a few pumps. And I say that with a lot of respect. We do a lot of those projects, but it means something.
Yeah.
It really counts for a lot of energy.
Okay, great. Thank you. I think it was really cool. I don't see any questions coming in. Maybe you do. I mean, I refreshed my chat, but that was about 10 seconds ago.
I have a question.
You have a question. That's great.
Yeah. I was interested, Paul. Thank you for that really interesting presentation. I had a question about the whether you, in your experience using renewable energy for these kinds of remediation systems, do you find it complementary or a hindrance? The sort of the relationship between the efficiency of the system and the amount of power you can put in through your solar panels. So I'm thinking, for example, if you had a system where your objective was to pump out groundwater, and during winter months, groundwater elevations are typically higher, and your requirements to pump would be greater to meet your dewatering target, but then in the summer, you've got more energy to play with. So I just wondered what your experience with.
Yeah, that's quite a good question, because we had a lot of discussion about it, because if you look in energy consumption or the productivity of a system, in this case, water abstraction, a lot of approvals for a remediation approach, they say 10 cubic meters per hour. They never say a certain amount per year. So there is already the approval of the environmental authorities on our approach. So if you, as a consultant, define an approach, it's maybe good to say that we achieve our remediation targets by a certain amount of water per year instead of per hour, because that already provides the flexibility to use other types of energy. And that same applies for a lot of other details about energy consumption. We are very much based how we write things down on a remediation approach, but also applying for approval by environmental authorities, are all quite hinged on the conventional thinking of cubic meters per hour, energy, etc., etc. But for remediation, that's not a point, especially in situ remediation. In situ remediation is aimed to improve the quality of the soil, do it within a certain amount of energy per hour. So that's indeed quite important. And what we have learned is that also with the water treatment, indeed some treatment efficiencies are lower in the wintertime, but overall, if you can still design that the efficiency rate is sufficient even in wintertime. That means just you have to have a more buffer capacity, so more margin in your system. But you can design for that. It doesn't make it more expensive. It just you have to design in advance. So adding more margin into your system to overcome seasonal effects is not more costly. It's just a thinking process.
Okay.
I hope that answers your question. It was a long answer, by the way.
Thank you.
Well, I think that was it. There were no questions from the audience. So we'll move on to Richard. So Richard, the floor is yours. You can share your